Hey everyone, and welcome. Today we're diving into a Leetcode problem called Find Closest Node to Given Two Nodes. It sounds a bit like a treasure hunt in a graph, doesn't it? We'll break it down step by step, so no worries if graphs seem tricky. Let's get started. So what's the goal here? We're given a directed graph with a bunch of nodes, numbered from 0 up to -1. The key piece of information is that each node has at most one outgoing edge. This list of edges tells us, for each node, where its single outgoing edge points to. If it points to -1, it means there's no outgoing edge from node. We're also given two specific starting nodes. Let's call them node 1 and node 2. Our mission is to find a third node. Let's call it the target node. That can be reached from both node 1 and node 2. Among all such reachable target nodes, we want the one where the maximum of the two distances, the distance from node 1 to the target and the distance from node 2 to the target, is as small as possible. If there are multiple such target nodes that give us the same minimized maximum distance, we should choose the one with the smallest index. And if no node can be reached from both node 1 and node 2, we should return -1. Let's walk through an example. Imagine we have edges defined as a list, 2, 2, 3, -1. This means node 0 points to node 2, node 1 also points to node 2, node 2 points to node 3, and node 3 doesn't point anywhere. Our starting nodes are node 1 equals 0 and node 2 equals 1. First, let's find distances from node 1, which is node 0. From node 0, we can reach node 0 itself in 0 steps. From node 0, we can go to node 2 in 1 step. From node 0 we can go to node 2, then to node 3, so that's 2 steps to reach node 3. Node 1 is not reachable from node 0. Now let's find distances from node 2, which is node 1. From node 1 we can reach node 1 itself in 0 steps. From node 1 we can go to node 2 in 1 step. From node 1 we can go to node 2, then to node 3, which is 2 steps to node 3. Node 0 is not reachable from node 1. Okay, which nodes are reachable from both our starting nodes? Node 2 is picture 1. From node 0 the distance is 1. From node 1 the distance is also 1. The maximum of these two distances is 1. Node 3 is also reachable from both. From node 0, the distance is 2. From node 1, the distance is also 2. The maximum of these two distances is 2. We want the smallest maximum distance. Comparing 1 for node 2 and 2 for node 3, 1 is smaller. So node 2 is our answer. Alright, so how do we approach this systematically? The core of the problem is about finding distances in a graph. A common way to find the shortest path in terms of number of edges, which is what we need here, is using a technique called breadth first search, or BFS for short. The fact that each node has at most one outgoing edge is a really helpful hint. It means that if you start at a node and follow the edges, you're tracing a single unique path. You won't have multiple choices at each step. This path might eventually lead to a cycle, or it might end if it hits a node with no outgoing edge. This structural property makes finding paths pretty straightforward. So a clear strategy emerges. First, let's figure out the distances from our first starting node, node 1, to every other node in the graph. We can use BFS for this. We'll store these distances. Second, let's do the same thing but starting from node 2. We'll run another BFS and get all distances from node 2 to every other node. Once we have these two sets of distances, we can go through each node in the graph, from 0 up to -1. For each of these nodes, let's call it candidate node. We check if it was reachable from node 1 and from node 2. If it is, we then look at its distance from node 1 and its distance from node 2. We take the larger of these two distances. Our goal is to find the distance is the smallest possible. If there's a tie, we pick the Alright, here's how we can write this in Python. Don't worry if it looks like a lot at first glance. We're going to break it down piece by piece. The main idea is exactly what we just discussed. Calculate distances from each starting node, and then compare them. First up, we have a helper function. Let's call it getDistances. This function's job is to take a starting node and figure out the shortest distance from that start node to all other nodes in the graph. It begins by creating a list, called to store these, well, distances. Initially it fills this list with -1 for every node, which is our way of saying we haven't found a path to this node yet, so it's currently considered unreachable. Then, it sets up a queue, which is essential for our breadth-first search. The distance from the start node to itself is of course 0, so we record that and add the start node and its distance 0 to our queue. The main part is a loop that continues as long as there's something in the queue. In each step, it takes a node and its current distance from the queue. It then looks up where this node's outgoing edge points to. That's our. If this exists, meaning it's not -1, and we haven't already calculated a distance to it, its entry in is still -1. Then we've found the shortest path to this. Its distance will be the current node's distance plus 1. We record this new distance and add the and its new distance to the queue so we can explore from it later. Once the queue is empty, we've explored all reachable nodes, and the function returns our list of. Now for the main part of our solution. First, we call our getDistances helper function twice. Once starting from node 1, to get a list of distances we'll call dist1, and a second time starting from node 2, to get distances we'll call dist2. We also need to keep track of the best result we've found, so we'll have a variable say min-max-dist, initialized to a very large number, infinity, effectively. This will store the smallest maximum distance we've encountered. And another variable, resultNode, initialized to -1, which will hold the index of the node that gives us this min-max-dist. Then, we loop through every possible node in the graph, using its index from 0 up to -1. Inside the loop, for each node we first check, is it reachable from node 1? We know this if its entry in dist1 is not -1. And, is it also reachable from node 2? Similarly, its entry in dist2 must not be -1. If node is reachable from both, we then calculate the maximum of two values, its distance from node 1, which is dist1 at index, and its distance from node 2, which is dist2 at index. Let's call this the current node max dist. Now we compare this current node max dist with our overall min-max dist. If the current one is smaller, it's better. So, we update min-max dist to this new smaller value. And we set our result node to be, what if they're equal? If the or asks us to pick the node with the smaller index. So, we check if our current node has a smaller index than the result node we're currently holding, and if so, we update result node to t. After checking all nodes, result node will hold our answer, so we return it. So how efficient is this approach? Let's talk about time complexity. Our 20 baked distances function, which uses BFS, will visit each node and each edge at most once. Since there are nodes, and because each node has at most one outgoing edge, there are at most edges, one BFS run takes roughly operations. We do this twice, once for node 1 and once for node 2. So that's like 2 times operations. Then, we have a loop that goes through all nodes to compare distances. That's another operations. Adding it all up, the total time is proportional to which we call big O of n, or order n. This is pretty good. What about space complexity, or how much memory we use? We need space to store the distances from node 1, which is a list of size, and space for distances from node 2, another list of size. The queue used in BFS can also, in some cases, hold up to nodes. So the total extra space we use is also proportional to or order n space. So, to wrap things up, what are the main ideas here? First, that special property of the graph, each node having at most one outgoing edge, really simplifies things. It means paths are straightforward to trace. Second, breadth-first search, or BFS, is a go-to tool for finding shortest paths when all edges are the same, like here, where each edge just counts as one step. And finally, the overall strategy was to break the problem into manageable parts. First, find all distances from node 1. Second, find all distances from node 2. And third, combine this information by checking every node to see if it's a good meeting point, keeping track of the best one according to the problem's rules. Hope that explanation made sense and helped you understand this problem a bit better. If it did, feel free to hit that like button, perhaps subscribe for more Leetcode breakdowns, or drop a comment if you have any questions or thoughts. And hey, if you're feeling extra generous, the Boba Fund is always appreciative. Keep on coding, and I'll catch you in the next one.